in our sol path here. Let's look at this first graphic. So to date, the rover has traveled 2.2 kilometers, or about 1.4 miles. And if you follow the path leg south, you can find the location of our first sampling attempt at Rubion. As we continued our leg to the west, we were very pleased to see our enhanced autonomous navigation system performance travel about 560 meters in just over the course of 2 weeks while performing remote sensing along the way. So we are well on our way with a fast traversing vehicle on Mars, making great strides. But let's talk about the sampling. So let's see our next image here. So this is an image of our first sampling location. Our target Rubion is on the right, and you can see this is a paver stone. And while we failed to acquire a solid core at this location, we believed it to be a result of the actual properties of the target. But we also needed to make sure that we didn't have a problem with the sampling system itself. So the engineering team, working with the project science team, sought out to reach a new target, and we nicknamed this target. We found a target which we believed to be less weathered and more robust, and nicknamed the target Rochette. So in this next image, you can see this target Rochette, and you can see the robotic arm placed on that target. Now, prior to sampling, we go through a series of pre-sampling steps. And here, you can see that the Watson image is actually observing different locations on the target to assess where we may want to core. On the right side of the image, you can actually see the coring tool, and it currently has an abrading bit installed. Now, we use this abrading bit to create a 5-centimeter patch and remove a few millimeters off the top of the surface so that we can see the internal structure of the rock and evaluate its composition with the science instruments that we have on board. Now, after reviewing the abrasion of this target, which we can see in this next image, the engineering and sampling team felt quite engineering and science team and sampling team felt quite confident about proceeding with an acquisition in this rock. And, as Lori mentioned, not only did we core and acquire and store one sample, but we acquired 2 rock core samples. As we were evaluating this target, the science team found this target to be a very high value as well, and we proceeded with our paired sampling strategy. And the second sample was acquired just 2 days after we acquired our first sample. So the height of each of our 2 rock core samples, the first was 5.9 centimeters, the second 6.1 centimeters, and with a target depth for acquisition being 6.6 centimeters, you can imagine we were all very, very pleased with these results. The volume is measured by an internal station inside the cavity inside the rover itself. So personally reflecting on this moment, this has been the culmination of so many years of so many people's hard work and time and effort. And I know that when I joined this particular project in 2014, I wanted to be a part of this moment, to be able to achieve something that has never, ever been done before. And while it definitely was a very long time waiting, I think all of us can say that it feels fantastic to be able to be up here and share this all with you. But of course, building spacecraft and operating them on Mars does not come without its challenges. But these are the challenges that keep us all going and motivated to do what we do, whether it's...
Then the robotic arm retracts from the surface and drops off the drill bit with the now filled sample tube into our sample processing center. There's a sample handling arm which manipulates the sample to take images of the sample, to measure its volume, to seal the sample tube, and then to store it on board for potential future return. In our first attempt to acquire a core at target Rubion, we commanded the sampling system to acquire and process the sample on the same sol or Martian day. For our second sample attempt at target Mont Denier, we wanted to do things a little bit differently. And what we did was we acquired the sample first, or attempted to acquire the sample first. We then paused before processing the sample so that we could confirm that there was a sample in the drill and in the tube. So next image, please. So if we look at the images on the left and the right, these images were acquired after we picked up the sample, but before processing. On the left, you can see a beautiful image of the core within the bit and tube. But on the right, it's not so clear that we actually have a core in the bit or the tube. So what happened between the left and the right? And the answer has to do with our process for acquiring a core. When the drill breaks off the core to capture it, sometimes we get a little piece of rock stuck between the sample tube and the drill bit teeth. In order to mitigate that, we point the drill bit at a bit of an angle, and we perform a couple brief percussion activities to try to either shake that little piece of rock out of the bit or to force it down into the tube with the rest of the core. The image on the right is after that procedure was executed. So when these images came down and we took a look at the one on the right, we knew one of two things had to have happened. Either our core sample was ejected out of the bit during that percussion activity, which we thought was highly unlikely, or our core sample slid down into the tube and we just couldn't see it due to the lighting conditions. So in order to not process an empty sample tube, what we decided to do was take an extra day, acquire additional images under better lighting conditions, just to verify that we had a sample. So just imagine we had a couple days of being anxious. We then met in our command center. We were huddled around our computer waiting for the images to come down. And then the next image, please. And then this is what we got. We were rewarded for our patience. So you see an image looking down the drill bit into the tube, and you see a beautiful core there. And at that point, our team was just absolutely ecstatic. I don't have words to say how we felt. Many of us have worked 8 years or more to design, build, and test this system, and this was just the fruition of our efforts, and we were just thrilled that it worked. But our job wasn't quite done. We had to process the sample. So we gave the go-ahead to proceed with processing the sample. Next image, please. So what we see here are a series of images at our vision station within our processing center. And you can see, as we move the tube up into the camera, our sample comes into focus. This is the absolute best view that we have of the bottom of the core. And we're rewarded once again with an absolutely beautiful image. After that was finished, we then had to seal the sample. Next image, please. So this is a before and after of the sealing process where we could see that it was activated. These images were taken again at our vision station. And then finally, we stored the sample on board. Now, the resulting core that we got was roughly 6 centimeters, which is about 2 inches, and it would look probably something like this one. This is a sample from our test program here on Earth. Well, Mont Denier was our first sample acquisition and processing. A couple days later, we processed our second sample at Montagnac on the same rock. But our job's not done. We have an additional 35 sample tubes to acquire samples and to process. So we have a ways to go, but we're excited to have the opportunity and we're thrilled to have the challenge. And with that, I'll pass it on to Katie.
Thanks, Matt. On behalf of the Mars 2020 science team, I would like to thank and acknowledge the thousands of engineers and scientists who contributed to this major mission milestone crater in the first image. We can see here the rover's landing site at Octavia E. Butler Landing, shown there in blue, and the rover's current location in green. Since landing, Perseverance has been exploring the rocks of the present-day floor of Jezero Crater. Scientists have long debated whether these rocks are sedimentary, perhaps related to the ancient lake in which the Jezero Delta was formed, or whether they were the result of volcanic activity in the region. Regardless of whether these rocks are sedimentary or volcanic, they've been of interest to the Perseverance team because they include both some of the oldest and amongst the youngest rocks in Jezero Crater. And these rocks have the ability to provide important time constraints and duration constraints on the Jezero Lake and its habitability, and aid in our construction of the geologic history of the region. Zooming into the rover's traverse thus far, as seen in the next image, we can see, as Jessica mentioned, that after the rover landed, we began traversing south, carrying out a dedicated campaign to study the rocks of the crater floor. We attempted our first sample of these crater floor rocks at a location called Rubion. Rubion happened to be one of the lowest elevation places traversed by the rover, which could have offered us our first clue that these rocks were weak and perhaps particularly susceptible to erosion. When our first sample attempt didn't go quite as expected, we decided that our second attempt should be in a setting that was very different, with rocks that had very different material properties. We then turned our attention to the resistant rocks up on the capping the cliffs and ridges nearby and past Rubion. We ended up traversing our 2B Ridge, a feature shown here in this image, and ascended the top of our 2B Ridge, where these massive capping rocks occurred, at a location called Citadel. When we arrived at Citadel, which we can see in the next image, this is the view that we had. We saw a series of blocks organized into a layer dipping about 5 degrees to the south. Although these rocks have been slightly displaced, they probably haven't moved too far from their original location. We were searching for a strong, hard rock that was big enough for both an abrasion as well as up to 2 drill targets. We found what we were looking for in a rock that we called Rochette, which you can see annotated in the next image. A side-by-side comparison of Rubion, the place of our first sampling attempt, and Rochette, where we successfully cored this week, can be seen in the next image. What we have here is Rubion on the left side, and we can see that this outcrop is low-lying and flat with rounded edges and a rubbly, crumbly surface texture. On the right, we have Rochette. It's standing up from the ground and has hard, angular edges, characteristic of hard rocks as we know them on Earth. And so we were thinking that also, if you look at Rubion, we can see that it is breaking down into pebble-sized grains. In contrast, Rochette is relatively smooth with flutes and grooves on its surface, suggesting that it has survived billions of years of wind erosion. Based on the observations that we have so far, we tentatively interpret Rubion and Rochette as ancient volcanic lava flows. We base this interpretation off of the lack of sedimentary textures, obvious sedimentary textures in the rocks that Perseverance has explored thus far, and in fine-scale textures that Yulia will talk about in a moment. Volcanic rocks are an exciting addition to Perseverance's sample collection because volcanic rocks have the potential to tell us about the interior workings of planets and are particularly good for providing the ages of rocks. An interesting thing about these rocks as well is that they show signs for sustained interaction with groundwater. If these rocks experienced water for long periods of time, there may be habitable niches within these rocks that could have supported ancient microbial life. Because these rocks were of such high scientific potential, we decided to acquire 2 samples here at Rochette. The Mars 2020 science team has a plan to acquire and to place down 1 or more sample caches. And so to ensure that each of these sample caches are as complete as they can be, we have a strategy to acquire two samples at each of our highest priority sampling locations.
Next slide, please. These abraded patches as this freshly exposed surface to look at the texture and chemistry of the rock using our onboard instruments. The next slide is a natural color close-up of a part of Bellegarde. That is our the most recent abraded patch made by SuperCam instrument. SuperCam uses optical and laser spectroscopy to identify chemistry and mineralogy of the rock. The image of Bellegarde here shows that the rock consists of several mineral phases. You can see them by color. They are light, white, dark, grayish, and somewhat rusty color. The overall chemical composition of Bellegarde is consistent with minerals typical for an igneous or volcanic rock. The rock originally solidified from lava or magma, such as basalt or gabbro. But in addition, Raman spectrometer of SuperCam identified a salt within the rock. And you can see that white speck right in the middle of the image. Further imaging by Sherlock instrument, you can see in the next slide, that instrument is placed within only a few centimeters from the rock surface. And it gives us even more detail. You now can see individual crystals, and some of them are angular or elongated, we call them tabular, and not rounded as you would expect in sedimentary rock. That observation further supports the hypothesis of the rock's igneous or volcanic origin. So let's zoom even closer. The blue square in the middle is a footprint of Sherlock's spectral analysis, and it's only 6 by 6 millimeter in size. The next slide shows that footprint. You really can see individual crystals here. And while the detailed mineral analysis are still ongoing and the science team working and poring over the data that is supplied by our Perseverance rover, Sherlock spectroscopy results reveal the presence of salts as well. Salts such as calcium sulfate. Those are yellow dots in the image. The calcium sulfate is something like gypsum or relative to gypsum. And a calcium phosphate. Those are the blue dots. Now, next instrument, Pixel, identified over 20 elements in Bellegarde. The maps, like you see on the slide, same size as the Sherlock's map, show the chemical composition of each individual mineral grain from which real mineral can be inferred. Here is shown a spectral signal from calcium in red, sulfur in green, and aluminum in blue. Combination of calcium and sulfur in the same spot indicates a calcium sulfate, yellow color in this image. And that location for sulfate and composition correlate directly with Sherlock findings. So what does this actually mean? What it means that we have collected a rock from the floor of the geyser crater that is igneous or volcanic in origin, and it has salts within it. The presence of salts indicate that this rock was subject to water. The water percolated through the rock, and as it percolated and evaporated afterwards, it's left behind the salty residue. And why the science team is excited about that is because this rock, once returned to Earth, once returned to state-of-the-art laboratories, it can be really interrogated